Okay, so let us start again the second part. Now, we ended up with the creation of the dictionary. Now, we wonder, but why do we have to create a dictionary? It is not enough to create a table with 2 columns, because this could be the same thing. This row, ID8 is matched to this number, ID5 is matched to this number. Or the other possibility is to create a table which has the row names and then 1 column. So the issue is what is the fastest option? Is better to search the ID here or to search the ID in a table with just 1 column and row names, or in a table with 2 columns? You see the point? Because they all are doing the same thing. Because it is true that here also ID 12 is linked with this number, because you can find it in row 12. Here it says that the row name 12 is in a table, and then this table has this value. And this is same thing here. There is this file which is called dictionary comparison. If you run this file compares the computing time it takes to search under the 3 options. So you see that even if my computer is very fast, then here it is measuring the computing time. Okay. And here, this is the answer. Here it says that if you use the dictionary, the time that you take is below 1 second. If you use a table, it takes 11 seconds, or it takes 9 seconds. What is amazing that the table with just 1 column is slower than the table with 2 columns. That was something that was unexpected for me. How is this instruction measured? With instructions, tick and talk. Let me tell you how they work. If you write tick, TIC, and then you do something, for example, okay, and then you do talk, then you measure the computing, the amount of time from tick instruction. So you put tick, a series of instructions, and then talk, and then you measure the computing time it takes. That's the idea. Or alternatively, in MATLAB, you have this run and time. And this run and time is something which is spectacular, because here there is an interface, a graphical interface, so you can have an idea of the amount of time each instruction takes. Moment, because now it takes some time to create this interface. Let us wait. So, for example, here in this example, there were 1 moment, because it is, I hope it is doing something. Come on. No, this is the branch manager. Yes, here it is. No, here it is. Here it is. This is the interface. Then it says with all the calls and the time that it took. Now, this is our dictionary comparison. And so we go here. go here, and this instruction took 10 seconds, 54% of the overall time. And then let us look here. You see the lines of code that are very expensive in terms of computing time are shown with a red. So you see this dictionary, searching inside dictionary here, dictionary, the creation of the dictionary, and then the output of dic. This is something which really takes really a negligible amount of time. On the other end, if there is a table and then you have to search for these keys, this takes much more time. And this all the other instructions. So this is something which enables you to understand what are your bottlenecks. Right? What are the instructions for which you really spend most of the time? And here the experiment was, here I've generated 1 million keys. You see, 1 million. And then here I have 1 million values. So 1 million keys and 1 million values. Then I have to search 1,000 values inside these 1 million. So keys to search are just a random sample from this 1 million. Now you have to see the values of this key. So you see, overall they are 1 million. You extract a subsample of 1,000, and then for these keys you have to know the associated value for the key. And then you say, okay, create the dictionary, my keys and values. So dictionary, this one has 1 million values, this dictionary. Moment, because it is 1 million. Okay, it is 1 million, you see. Here it shows just the first and the last. So to each string it has associated a value. So you have to search 1,000 keys, and then you have to find the corresponding 1,000 values. Therefore, you do it with the dictionary, you survive. You do it with the table, you can have a coffee, you can have a cappuccino, or you wait much more than you wait to be enrolled. Sorry about that. So just, I mean, I want to put it as a joke, but it is not a joke. I fully understand. Okay. So this MATLAB profiler. Okay. Now it is time to see the linear algebra. I assume that you all know about matrix multiplication. Tell me. Right. Tell me if, okay, if C11 is what you expect. Let us review it. So this element here, therefore, is 3 times minus 1 plus minus 3 times 7 plus 9 plus 9 times 0. And this is this element here. So, if you have two matrices, A, the first matrix A is 2 times 5. First matrix A is 2 times 5. The second matrix B is 5 times A. What is the size of the product, A times B? 2 times 8, okay. Okay, so the product of two matrices has a number of rows which is equal to the number of rows of the pre-multiplying matrix and the number of columns which is equal to the post-multiplying matrix, right? The matrices must be conformable. That is, the number of columns of the pre-multiplying matrix must be equal to the number of rows of the post-multiplying matrix. So then that said, if I have x which is equal to 4, 8, and then if I have y which is 1, for example, yes, 1, 3, let us do set font size, set font size 14. So x times y is which dimension? One times one, okay? 1 times 3 times 3 times 1 is 1 times 1. 34. Yeah. On the other end, y times x is what? Which dimension? Of course, 3 times 3. Okay? Right? Are all these things clear? So 1, then multiply by 2, 4, 8. Then the second multiplied by 2, 4, 8. Third element multiplied by 2, 4, 8. Okay? And tell me something about the rank. You already know about the rank of a matrix. I want to know how much you know about linear algebra. The rank of the matrix is the maximum number of rows and columns which are independent. So the rank of this matrix is 1, because you see that the second column can be obtained multiplying the first column by a constant. The third column can be obtained by the first column multiplied by a constant. Similarly for the rows. Okay. So the rank is 1. Now, there are special matrices. And these are these diagonal matrices. For example, diag 1, 2, 4, you see that creates this diagonal matrix. Okay? Or, so therefore, this diag function, if you supply a vector, it creates diagonal elements. It creates diagonal elements with the elements on the main diagonal. Or if you write 1, it creates a matrix which all the elements in the vector and are in the diagonal just above. You see? So if you put 2, the elements are 2 in the second diagonal above. Same thing for -2. Okay? So, for example, this syntax, what is going to create? That 1, 2, 4 here is created both in the diagonal above the main diagonal and below the diagonal below the main one, right? On the other end, let us suppose that your magic matrix A, and then on the other end here I say diag A. Now the input is a matrix. Okay? What do you expect it does? Now it extracts the elements in the main diagonal, right? So if A is this one, diag A2, what do you expect? No. 1, 14, and 22, eh? Okay, you got it? So two diagonals above the main. Okay? And -1. So if I have A, you see, -1, the elements just below the main diagonal. You see? So if the input is a vector, it creates a diagonal matrix. If the input is a matrix, it extracts the elements in the main diagonal or the diagonals above or below. Then everything, of course, diag, then you type F1 and then you go into the help. You see, so create a diagonal matrix or get diagonal elements. These are the two things. You see, create a diagonal matrix or get diagonal elements, depending on the input. The input is a vector or the input is a matrix. So the identity matrix is a special case of identity. Then in MATLAB there is a function which is called gallery. Okay, and then gallery, and then you can have tons of matrices that are well known in linear algebra. For example, let us say min ij of size 5, min ij is a matrix such a way that the element is the minimum of the height and jth row. So if you are in row 3 in column 5, then it writes 3. If you are in row 3 in column 5, the minimum of row and column. So gallery and then circle of size 6, the circulant matrix. You see, there is this, they circulate the elements. You see? Can you see that it circulates from each row? So with this gallery, here you have just take the matrix name, and then here there is really the word. Well, you can see them also from a graphical point of view. But here there is, at the end, there is, you see, I don't even know all of them. But there are really tons of matrices. Okay. Now, linear systems of equations. Okay, also this, of course, you know how to solve them in using pen. Of course, I mean, now, do you all agree that this linear system of equation can be written in this way? Okay, try to do the matrix multiplication of A times X. You see that this is 3 times X1 plus 5 times X2 plus 4 times X3. You can see it's this one here, equal to 25. Therefore, the multiplication of the first row of matrix A with vector X equal to 25 is just the first equation. On the other end, 2 times X1 plus 10 plus X2 plus 1 plus times X3 is equal to 25 is the second equation. and similarly the third equation. So this is the system of linear equation put into matrix form. Given that there is AX is equal to B, X is the inverse of A times B. That's the solution, right? Because inverse of A times A gives what? In general, if you have a matrix, this X matrix run then 3 times 3. Inv of X is the inverse. Inv of X times X is what? The inverse of X times is what? Yeah, of course it is the identity. Yes, correct. Of course, this plus and minus probably, because if you put format long, maybe there are, yeah, no, here there aren't, but maybe there are decimal places, I mean, but it is, yes, it is, this is the identity. That's the reason why here you multiply both sides by a to the minus 1, and this is the identity. The identity times x is x. That's the reason why here, when you multiply both sides by a minus 1 times a is the identity times x is x. On the other end, you have multiplied by the inverse of a, so a minus 1 times b. That said, if the matrix is 3, 5, 4, the matrix here, the matrix A is 3, 5, 4, and then 2, 10, 1, 2, 2, 9. 2, 10, 1, 2, 2, 9. B is equal to 25, 25, 20, 33, 25, 25, 33. Okay, let us make a check. This is A, and this is B. Right. X is equal to inverse of A times B. So X, so let us go back to format short. X is equal to 1, 2, 3. Let us make a check that X is equal to 1, 2, 3. 3 times 1 plus 5 times 2 plus 4 times 3 is equal to 25. So, okay, if you plug in the values of 1, 2, 3, then you get these 3 equations. Okay, in order to compute be able to compute the inverse, the system must be in such a way that, in order the system not to have an infinite number of solutions, you must have the determinant of the coefficient is not equal to 0. Right, if the determinant is 0, means that one row is a linear combination of the other, or one column is a linear combination of the other. So the determinant must be different from 0. If you try to solve here in this way, it says that, yes, you can do it, but this is slower. And MATLAB suggests to do it with A\B. So this is how MATLAB suggests you to compute A\B. This is the syntax of MATLAB. There are also the shirts. If you see in summer a person with A/B, this is a MATLAB user. And I hope also this year, people who will get the best 3 exams will receive the gadgets from Matters, as we did in previous years. What they will give me last year they gave me a shirt, then other things, then the best 3 exams will get these gadgets. So you can, so on the beach, so you can you can show them. Okay. So the system of equation is called homogeneous if this b is equal to 0. If the system is homogeneous, that if b is equal to 0, the system ax is equal to 0, a vector of 0, always has the solution x is equal to 0, clearly. The only one possibility for which you don't have this trivial solution is that the determinant of A is equal to 0. And this is the key issue for the eigenvalues, eigenvectors concept that we are about to see. Okay? Now, before we go into that, element-wise matrix operations. So we have seen that times is matrix multiplication. Now, suppose on the other end that you have this x and y. Let me come, for example, suppose now that y is equal x plus 10 or whatever. So here you want to multiply each element of x by each element of y. If you do x times y, it works? Absolutely not. Matrices are not conformal. Right. Therefore, here it suggests if you want to operate on each element of the matrix individually, use dot star. Okay? Similarly, if you let us do x is equal to x prime, x square works? Not at all. If you want to use erase each element individually, then dot. So this one works, right? So here, if you want to compute, for example, the standard deviation of this thing, I don't know, shall we do it together or can we skip it? How do you compute the means? So the means is the weighted mean. Okay, this is the frequency distribution. So each element of x must be multiplied. This is the formula here. And this is the standard deviation. Can I skip it or okay, I can skip it. Okay. In what follows, the notation that we are going to use is x, our original data matrix, which is n times p. If it is a table, we are going to use generally xt to denote that it is a table. On the other end, x tilde is the matrix of deviations from the means. Right? On the other end, Z is the matrix of zeta scores. Okay, let me say something, and for example, x is run then, for example, n times p, n times p times 3 plus 10. Okay, let us suppose now that n is equal to 20 and p is equal to 3. So this is our original data matrix. Our original data matrix, which contains the rows, the units, and then 3 variables. Now, if I have to compute the deviations from the means, matrix of deviation from the means. Of course, the means are, or let us call average x, so mean of x. Okay, mean of x you can have all to compute the mean of all elements. You can, on the other end, have a number here which says whether you want to work with the columns or with the rows. So therefore, this x1 computes the mean of the columns. Mean x2 computes the means of the rows. Right? The mean of each row. On the other end, if you put 1 here, it computes the mean of each column. Now, the mean of each column is 1 times 3. The matrix here is 20 times 3. If I do x minus average x, you see this one is 20 times 3. This one is 1 times 3. So strictly they are not conformable. 20 times 3 minus 1 times 3. So therefore, if you do it in MATLAB, there is the so-called automatic expansion. The automatic expansion, then that is put untitled, is automatic expansion, and then it does the job. It expands average in a n times p matrix, and so every column is as the mean each move removed. Right? Now, what is the mean now of each column of x tilde? So this is the original matrix. The original matrix now has the averages. Now you have removed to each column the averages, and then you have a new matrix, which is x tilde. The matrix for which to each column you have removed its mean, the mean of the column. So now the mean of x tilde will be what? The mean of each column. Tell me. No, the mean. Now later we deal with the standard deviation. You see, now I have to each column I have removed the mean. To the first column I have removed the mean of the first column. To the second column I have removed the mean of the second column, and for the third column I did the same. And then I get a new matrix, which is called x tilde, which is called the matrix of deviations of means. This matrix has the same size of the original matrix. So the original matrix was 20 times 3, and this new matrix is 20 times 3. So matrix of deviation from mean, n times p, if the original matrix was n times p. Now, 0, of course, all of the columns will be 0, clearly, yes. The mean of x tilde, comma 1, and so this is m x tilde, call it. And you see that indeed it is 0. It is these numbers times 10 to the minus 14. Okay, you don't have to expect exactly 0. You have to expect something, a small number, which is of order 10 to the minus 14. And this is the order of precision of MATLAB, Python, whatever, right? Right. Now let us see the standard deviation of x. The standard deviation of x. So if I, let me be here more precise. if this syntax, the means of matrix X, I could have done here in this way, without any number. Okay? So, if you don't do anything, the mean of the matrix is meant the mean of the columns of the matrix. Right? On the other hand, if you do the mean of these three elements here, then it computes the mean of these three elements. So you have to be careful. Okay, so it is always better to specify if you want to do the mean for column or for rows. Okay, now the mean, these are their means. Okay, now let us put a random seed so that the results will always be the same. The numbers will always be the same. Now, this is a standard deviation, for example, sigma equal std of x. These are the standard deviation. This is the syntax. These are the standard deviation of the original columns, right? Now, the standard deviation, the STD in matrix X tilde, how will they differ from the standard deviation of the original matrix? You have removed the means, okay? So you compute the standard deviation to the original variables or to the new variables which have mean 0. How will the standard deviations change? If they do. Okay? What will be the vector of new? These are the new sigma. Okay? I run it. Now, the original sigma were these. And the new sigma, the sigma absolutely remain the same. You can do a translation of each column and the standard deviation is the same. And this is, it is very clear. It is very clear from here. So you take these deviation from the means, and in the deviation from the means, they have mean 0. The new mean will be 0. So you have already removed the mean or whatever. You can, if you add 20 to x, you add 20 to the mean. So you can move around, you can shift, and the standard deviation will remain the same. So the location will change if you add or if you subtract something, but the scale will always remain the same, right? Then there are the so-called zeta scores. Zeta scores are the, in mathematics, is x minus the mean divided by the standard deviation. That is the zeta scores. So, let us see how to compute this matrix Z. Z is equal to x tilde. Now, each column, the first column has to be divided by the standard deviation of the first column. The second column has to be divided by the standard deviation of the second column, and so on and so forth. Now, this sigma is 1 times 3. And the x tilde is 20 times 3. You see the point. 20 times 3, and then you have 1 times 3. So the first 20 value of the first column you have to divide by the first element of sigma. Second column divided by the second element, and so on. Okay. Therefore, here, something like that. Well, it has worked with the, it has created a column vector. No. This is not what we want to do. We want to division elements by element. Element by element. But sigma is 1 times 3. This is 20 times 3. So it automatically expands sigma in a 20 times 3 matrix and does the job. Okay, so this is the Z scores. Now, the mean of Z is what? I have this matrix. 0, 0, 0. Let us check it. Yes, 0, 0, 0. Now, the standard deviation, the vector of the standard deviation of Z. Yeah. Now, this time, the vector of standard deviation will be 1. Right, so we have transformed each column of the matrix into new columns that have 0 mean and standard deviation is equal to 1. Not only, but these Z values are pure numbers. They do not have the unit of measurement of the original numbers. They are pure numbers. They are unit-free measurements. Okay, that's it. Therefore, this implicit expansion, which is described in section 2.7 of the book, does this thing. That is, similarly, this instruction here does what we were expecting. That this instruction creates the matrix of zeta scores. Now, the function which automatically create the zeta scores is called zeta score. Okay? Zeta scores automatically does everything. Okay, now I want to check whether Z and HK, every time that I write CHK, I mean check a different way of computing that particular result. Now, it is true that it is equal Z or ZCHK, maybe not, let us see. No, this time it is true. Okay, now let us maybe put bigger numbers. Yes, it works all the same. Right, let me remove. The precision is incredible. Okay, they are exactly the same. Sometimes you have to check that they are equal up to 10 to the minus 14. This is the issue, right? So the equality of doubles is always a bad idea to check the equality of doubles because they have a huge number of decimal points, decimal digits. Okay, now, so these are the z-scores. So you remove the mean and then you divide it by the standard deviations. It is clear that if there are outlying observations, to compute the means is always a bad idea. Instead of the means, you have to compute, for example, the medians, if there are outlying observations. Similarly, if there are outlying observations, to compute a robust variability index, you don't have to compute the standard deviations, but you have to compute the robust MAD. So the median of the deviation from the medians. So for example, now, let us load the cities Italy. Load cities Italy.
What is robust? What is robust?
Why is robust? Because why the median is robust, or why the...
What is robust? Because like, I did not hear the word robust before.
Ah, right. Okay. So now I will, I've become a professor of statistics thanks to my papers in robust statistics. And in fact, our interdepartmental center, which is called ROSA. ROSA stands for Robust Statistics Academy, experiencing robust analysis of big data. So, robust analysis is the analysis which is not affected by the presence of outlying observations. So there are regression, multivariate, machine learning model, or whatever that are robust to the presence of outlying observation. So, for example, it is much better to compute the median rather than the mean as a very simple thing, because if you change one observation, then the median will remain the same. On the other hand, with the mean, it is enough that one observation is wrong, goes to infinity, and the mean goes to infinity. In mathematical terms, we say that the mean has a breakdown value of 0, breakdown point of 0. On the other hand, the median has a breakdown point of 0.5. That is, you can put to infinity all the values that are greater than the median. And the median remains the same because it's a central observation. So it's a robust measure. Similarly, the observations which are below the mean, below the median, can be moved up to minus infinity. And the median always has the order, the central observation. And same thing in regression. You have data that are not affected by the outliers. But for example, if you write FSTA outlier detection and robust regression in MATLAB with the FSTA toolbox. And you see that if there is one outlying observation, you see the regression line that is affected by this observation. On the other hand, you want that your regression line stays here, and if you do this fit, the regression line stays there, is not affected. This is the non-robust. This is the robust that stays, that is independent on the fact that here there is an outlier. Right. So this is our field of research, robust statistics. Now we give you just the basic ideas, the basic ingredients. Okay, you want to know more monitoring book. This is GitHub. This is a scientific book with all the YouTube videos, and then okay, this is the book. Applied robust statistics through the monitoring approach. Okay. Right. So this is the Springer-Verlag book all over the world that deals with these things. And then here is the source code on GitHub. And this is free. You see, download. This is absolutely free. After working 3 years, and then this is free. So here, in this case, we wanted that it could have the largest possible diffusion. Now, so thank you for asking. At least from time to time, I can talk about my research activity. At least 3 minutes. At least. Thank you very much. Thank you very much for asking that. At least you have to know what your teacher does from morning to evening, apart from now the administration and these things. Okay, so let us see an example. Load Cities Italy. So you load the Cities Italy dataset. Let us close all, clear all, and let me. Okay. So, okay. Now we do, for example, you see this is the unemployment rate. Suppose that there is an error. So first of all, let us do Z-score Cities Italy. It works with the table Z-score. Z-score, if there is a table, does not work. Okay. Our function Z-score fs still works, but this function, our Z-score fs, which is of the FSDA toolbox, what it does the robust Z-scores. That is, removes the median and divides by the robust measure of standard deviation. However, so Z-score fs, or for example, okay, so let us say the purpose is compute Z-scores non-robust. So if you do Cities Italy minus mean di Cities Italy, mean di Cities Italy, here the mean of a table creates a table, you see. So here you are doing a table minus a table. Works this syntax because these are two tables. One is 103 times 7. Yes, these things works because these two things have the same table name. You see, mean Cities Italy has the same names of the original table, and so it works. And so this is, let us say, x tilde. Now, if I do x tilde divided by std, Cities Italy, it works. X tilde unrecognized, okay. So, x tilde, standard deviation of Cities Italy, and so it still works because you have the same numbers, the same column, the same name of the columns, the same variable's name. Or otherwise, there is this function which is called normalize. Normalize Cities Italy, and then here it says, what do you want to do? Here I want to compute the Z-score. Z-score, and so let us try this Z is equal, and that's it. Normalize. So avoid all these things, and then with the normalize. Now, let us suppose that you have, for example, a value which is wrong. Cities Italy, let us say that the first row, all the elements of the first row are equal to minus 300, something like that. Okay? So you have cities Italy, so you have replaced with minus 300 the first row. When you compute the z-scores, now z, you see, you have this one which is equal to minus 3447, and then you see that these all are affected by these outlying observations. But if you put instead of this one, you put this, what happens? Minus 30,000. See, minus 6, but let us exaggerate. If you put all these things, you see that this is minus, this is the only one which is negative, and all the others are positive. You see, that's the problem. That all these z-scores are affected by this outlying observation, because you have a mean which is not representative, a standard deviation which is not representative. So it is true that the sum of this is 0, but in order to have this constraint, in order to have that the sum of this element is 0, one must be very large and negative, and all the others must be positive and small. So the mean of z is still 0, but the price that you have to pay is that all numbers are wrong. On the other hand, if you write z robust is, which is equal to z score fs di Cities Italy, z robust, this z robust. Now if you go here and if you see the matrix of robust, you see that still shows here, but all the others are centered around 0, right? So your outliers remain the outliers. All the others are really, you see, below or above 0. Right. On the other end, with Z non-robust, this one is negative and all the others are positive. You see, that's the issue. So, always use robust statistics. Now, the norm. The norm of a vector. The norm of the vector, you take the sum of squares, right? And then you divide it by the square root. In the Z matrix, the norms are all the same. So in geometric terms, these vectors, if you work with Z scores, you work with vectors, they all have the same length. So this variable, geometrically, is work with vectors that have the same length. This is the Euclidean norm. And you understand this notation, x prime x. Can you see that x prime x is the sum of square? Can you see it? Because x is a column vector. So row x prime times column is the sum of squares of the elements, right? Can you see it? Now, the general norm is that you raise all the elements to a power k and then you divide it by 1 over k. Now, the general norm, what happens when k goes to plus infinity? You end up with the maximum. If k goes to minus infinity, you go to the minimum. Okay, during the lab section, you ask everything, not only about computing, but also about mathematics, if you want to have all the proofs. And now, I'm not gonna show you all the proofs, but I'm very happy, so that you can see that I'm much better with mathematics. Okay, this is what I've always studied in my life. So there is this file norm k that computes all the norms. For example, given this vector, and then you compute all the norms. And this is the p is equal to 2 is the Euclidean norm. And then as an exercise, you put it in vector form. Now, the inner product, given these two vectors, this is the inner product, the dot product, inner product is this. So, two vector x and y. When you say two vectors, n times 1, n times 1. So, x prime is 1 times n, and y is n times 1. X primes times 1 is summation of xi times yi. Can you see it? Tell me. Okay, now, this inner product, geometrically, what does it correspond to? Well, if you have these two vectors, y and x, and then you have the angle among them, the cosine of the angle is the inner product time divided by the two matrix norms. That's the interpretation. Therefore, if you work with vectors that have norms equal to 1, the cosine of the angle is just the inner product. The cosine of the angle. Therefore, if the two vectors are perpendicular, 90 degrees, what is the cosine of 90 degrees? What is the cosine of 90 degrees? What is the cosine of pi divided by 2? Okay, no, don't check it in internet. What is the cosine of 90 degrees? What, how much? No, it's 0. Anyway, you check it. Cos in degrees of 90, and this is 0. Okay? So the cosine of pi divided by 2, okay, okay, so the cosine of pi divided by so pi is okay 360 degrees. So the cosine of 90 is cosine of pi divided by 2, then it is 0. So not the cosine, this cosine in radians, right? So the cosine of pi divided by 2 is 0. Or the cosine of 90 degrees in degrees is 0, right? Therefore, it is important to understand this geometrical interpretation. But this, this thing here, so the cosine, so this is x tilde, so the dot product between the column I and column J divided by the norm, this is nothing but the correlation coefficient. You see, the cosine of the angle is this, but this is the correlation coefficient. For when you compute the correlation coefficient among two variables, you compute the cosine of the angle between these two vectors. Right. If the two variables are roughly independent, then their vectors are orthogonal. They have a degree which is roughly 90 degrees, the angle among them. If the variables are highly correlated, then their vector will have an angle which will be very, very small. On the other hand, an angle close to 360 degrees means that the two vectors have a correlation which is equal close to -1. So that's the thing to understand, this geometrical interpretation. Now, how do you plot the vector? With function quiver. Quiver is the thing where you put the arrows, that's the quiver. Have you ever seen the Indians they have the quivers, then they have the arrows, they take the thing that they have behind, then they take the arrows and then they, okay, that's the quiver. So, and then here there is exercise 2.20. Let me home and then layout Marco. Sum of two table, then yeah, example of orthogonal vector. So let us try to have quiver vector which starts in 0, 0, then ends up with 2, 4. Right? Okay. 0, 0, and then 2, 4. You see that it doesn't go up to 2, 4, because there is a scaling. So in MATLAB, so you have to put the fifth element equal to 0, and then it goes up to really 2 to 4. So here the example of orthogonal vector. Orthogonal vector are vector whose angle is 90 degrees. And this is an example of orthogonal vector. Let me put here axes equal, so to have the same scale, so you can really see the perpendicularity among them. Okay, 90 degrees angle. The cosine is 0. The vector are orthogonal. The variables have no correlation. Now, and then quadratic forms. What is the geometrical interpretation of these quadratic forms? And then this sum of squares, weighted sum of squares, can be written, as you can see here, as what is called a quadratic form. That is an expression of this form. A row vector times a matrix times a column vector. Have you already done these things? Have you already heard about these things or never? Never? I hope during this data science course you will see them. But this quadratic form, this is really the first time that you hear it. But what is amazing is that here with the Copilot, yesterday I tried, write and weight the sum of squares as a quadratic forms. And then this is the code that it produced exactly, that was exactly my example. It's incredible, eh? You see, this look, x transpose yx. Right, this is the weighted sum of squares. In other words, this weighted sum of squares, lambda I times xi square, can be written in this way. Can you see if you do the matrix multiplication, then you have x1 times lambda 1, and then all 0. Then you have x2 times lambda 2. And then here you have 1 times n times n times n. If you multiply this one with this one, you have n times 1. N times 1 times n times 1. So the result of this is 1 times n. The result of the multiplication of these two, 1 times n, because it is 1 times n times n times n, 1 times n. 1 times n times n times 1, 1 times 1. So, these are 1 times n times n times 1, the result is 1 times 1. 1 times n times n times n times n times 1, the result is n times 1. 1 times 1, which is this. So writing this or writing this is exactly the same things. Right? But what is, and then you can try MATLAB, then you have this, so therefore 1 square times 2 plus 2 square times 3 plus 3 square plus 4, you can write it in this way, weighted sum of squares. And this quadratic form, for example, let us see. So therefore, this is the same thing as before. Now, what is the geometric figure of a quadratic form? Because everything has got a geometric interpretation. The quadratic form is a conic. Have you ever heard about a conic? A conic is a general thing for parabola, hyperbola, circle, or in 3D is a quadric surface, an ellipsoid, a paraboloid, an hyperboloid, a cone, a cylinder, and so on and so forth. Therefore, sometimes this quadratic form, independently of the value of vector x, the result is always a number that is greater than 0. It's something amazing. So independently of your vector x, in your vector x you can put any number, but the result of the quadratic form is a scalar which is greater than 0. If this is the case, then we call the matrix A positive definite, and then all the covariance and correlation matrices are positive definite. Something which is amazing. This is incredible. Well, this quadratic form is a conic, and this is the equation for the conic. So, if A is positive definite, then this equation defines an ellipse or an ellipsoid. And this is really fascinating. These are quadratic forms. Here, in these quadratic forms, you don't have these two terms, and then you have that this f is always smaller than 0, because if you put it in the right side of the equation, becomes greater than 0. And this is the condition to define an ellipse, when the conic becomes an ellipse. So the quadratic form, if our A matrix is positive definite, is always an ellipse. That is, when you cut this with this plane, you end up with an ellipse, not with a parabola, not with the hyperbola. This is something which is fascinating. And then, so the summary is that all these things are quadratic forms. Then if the determinant is greater than 0, and the determinant is what? The determinant is a function of the volume of the ellipse. Is incredible, eh? Or the determinant is a function of the volume of the ellipsoid. And then even if you find the multivariate normal distribution, has a quadratic form here. So the equidensity contours are indeed the ellipses in the multivariate normal distribution, but we are going to see it later. Okay, now, vector spaces. Vector spaces, you have these vectors, then you add them, you multiply, and the result is still a vector. In fact, you combine, you have this sum, this multiplication, you elongate the vector, but the vector remains vectors. And this is a vector space. So, in this, you have the concept of linear dependence and linear independence. If y can be expressed as a linear combination of this vector, then we say that y is linear dependent. If on the other end if you have this equality and this equality is true, just in the case where all the coefficients of the linear combination are 0, then we say that these linear vectors are independent. They all have 90 degrees. They are independent. I mean, they form these so-called bases. Now, let us see, these two vectors are linear independent. It is true that the only one possibility in such a way that their linear combination is 0 is that you have to multiply by 0 to obtain 0. If you multiply the first vector by -2, and then you add x2, -2x1 plus x2 is equal to what? -2x1 plus x2. -2x1 plus x2 is equal to 0. Right. So these vectors are linear dependent. And in fact, one is double the other. They are dependent. And the rank and is the maximum number of rows or columns that are linearly independent. Okay, or if you want to use the copilot, now generate a 3x3 matrix with rank 2. Well, it creates, you see, the third row is a linear combination of the first. In this case, exactly equal to the first. At least the copilot could have put at least here 2, 4, 6, at least a linear combination of the first row. Now, what is the rank of the matrix below? What is the rank of this matrix, in your opinion? The rank of this matrix, I leave you for exercise, is 1, because the second column can be expressed as a multiple of the first, the third column, and vice versa. Now, you have particular vectors that are called basis vectors, that they are independent, and the basis vector is a set of vectors which is linearly independent. And for example, in 2 dimensions, if you start from these two vectors, 1, 0, 0, 1, you can obtain any vector, right? Because you have multiplied the first column, the first coordinate by the number you like, the second coordinate by the number you like, and then you can obtain any vector in the 2-dimensional space. And you can generalize it to p-dimensional space. So these two vectors, these two elementary vectors, form a basis in R2. And these vectors form a basis in the in this case in the n-dimensional space, if they are n, and they all have length n. Now, an important thing is to understand how to change the basis. For example, you see these are the Cartesian axes that we are used to see, E1, E2, the canonical one. And these are the coordinates in these 5, 1, 5, 1, right, these 1.7, 3.5. Now, I mean, because we are used to these Cartesian axes, but the axes could be here, the black ones. Why not? This is a possibility. Sometimes it is better to put the axis under the direction of maximum variability. And this is the concept of principal component analysis, when you have to reduce the dimensions. Therefore, if you have these two basis vectors, what are the coordinates of the vector in the new basis? Because V1 and V2 are orthogonal. Same thing as before. And so, here you have these these are the coordinates in the new basis, and this is after you rotate, and V1 becomes this, and V2 becomes the new system, the new reference system of axes. Right, and all these things are implemented in these exercises. So from the, here you simply have to do a multiplication of two matrices. When you do the multiplication of two matrices, you change the basis. You go from one reference system to another reference system. This in practice, you see, something which is matrix multiplication. No, you change your basis vector. And how is chosen this new orthogonal system? This is something that we are about to see. Now, I don't have because eigenvectors and eigenvalues are a crucial thing. That is better if next time we start with eigenvalues and eigenvectors. In the meanwhile, if you want to go to this web address, then you can find it in the book. Then you start seeing these things, the concept of x and a times x. This is the vector, and then you pre-multiply it by a matrix. When they are aligned, where they are aligned, then we say that you have found the eigenvectors and eigenvalues. Okay, but this is just to give you an idea, because this is really fascinating. Okay, let us stop here. Thank you for your attention. So see you tomorrow. Tomorrow you do whatever you like. If you don't do the exercise of the book, if you wanted to have something more from the mathematical point of view, you can do. You ask everything. So we see again at 1:30 tomorrow. Thank you.